Imagine you have a machine that takes a number, does something to it, and spits out another number. A graph is simply a picture of every input-output pair that machine can make. To draw this picture, we use a flat surface called the Cartesian plane. It's built from two number lines that cross at a right angle. The horizontal line is the x-axis, and the vertical line is the y-axis. They meet at a special point called the origin, which is the address 0 on both lines. Any single point on this plane is just a pair of numbers, written as x, y, telling you exactly where to stand, how far to walk along the x-axis, and then how far to walk up or down parallel to the y-axis. Why bother drawing a picture when you could just calculate numbers? Because a list of numbers is like looking at a mountain through a keyhole, you see one rock at a time. A graph shows you the entire mountain. It lets you see the shape of the relationship. You can instantly spot where the function is climbing, where it's falling, and where it turns around. This is incredibly powerful. If you know the shape, you can guess what happens between the points you calculated, and even predict what will happen far beyond them. In physics, this is how we understand a ball's flight. In engineering, it's how we design a smooth road. The graph answers the big question: if I nudge the input a little, how does the output behave? Let's build one. A function, often written as f of x, is just a rule. You feed it an input, x, and it gives you back an output, f of x. To make a graph, we pick an input, say x equals 1. We calculate the output, maybe f of 1 equals 2. That gives us a pair, 1, 2, which is a single dot on the plane. We do this again for x equals 2, getting a new dot. And again for x equals 3, and so on. We also do it for x equals 0, and negative numbers. Each dot is a little piece of evidence. When we have enough dots, a pattern emerges. We connect them with a smooth line, and that line is the graph. It's the visual shape of the rule. The word graph comes from a Greek word for drawing or writing, and that's exactly what we're doing, drawing the rule's behavior. Let's use a graph to solve a real problem. You toss a ball straight up. Its height in meters after x seconds is given by the rule 20x minus 5x squared. We want to know its maximum height. Instead of guessing, we build the graph. First, we make a table. At x equals 0, the height is 0. At 1 second, it's 20 minus 5, which is 15 meters. At 2 seconds, it's 40 minus 20, which is 20 meters. At 3 seconds, it's 60 minus 45, back to 15 meters. At 4 seconds, it's 80 minus 80, 0 again, it's hit the ground. We plot these 5 points on our plane and connect them with a smooth curve. The curve goes up, reaches a peak, and comes down. We can see right on the graph that the highest point is at 2 seconds, where the height is 20 meters. The graph didn't just give us one number, it showed us the entire flight of the ball. Imagine you're walking along a hilly path, the graph of a function. At any moment, you feel the ground tilting under your feet. The derivative is exactly that, the steepness of the curve at a single point. It's the slope of the straight line that just kisses the curve there, called the tangent line. If the curve were a roller coaster track, the derivative tells you how fast you're climbing or dropping right now. We write it as f prime of x, or dy dx, both mean the same thing, the slope at that instant. Why do we care about the slope at a point? Because it answers the most practical question in calculus: how fast is something changing right now? If the graph shows your distance from home over time, the derivative is your speed at each moment. It tells you where you're speeding up, slowing down, or standing still. It also finds the highest and lowest points, the peaks and valleys, because right at the top of a hill, the slope is 0 for an instant. Engineers use this to design safe roads, economists to find maximum profit, and physicists to predict where a ball will land. How do we actually find this instant slope? The trick is to zoom in closer and closer on a point until the curve looks almost perfectly straight. Then we measure its rise over run, just like slope on a straight line, but for an incredibly tiny step. If the line tilts upward to the right, the derivative is positive, meaning the function is increasing. If it tilts downward, the derivative is negative, and the function is decreasing. And if it's perfectly flat, the derivative is zero. That's a peak, a valley, or a flat plateau. The sign of the derivative is a simple detector. Positive means rising, negative means falling, zero means level. Let's see this in action. Picture a ball thrown straight up. Its height over time makes an upside-down U shape. On the way up, the graph is rising, so the derivative, the slope, is positive. At the very top, for a split second, the ball hangs motionless, the graph peaks, and the slope is exactly zero. Then on the way down, the graph falls, so the slope is negative. If the height function is h of t equals 20t minus 5t squared, the derivative at t equals 1 is 10 meters per second upward. At t equals 2, it's 0, the peak. At t equals 3, it's negative 10, falling back. The sign of the derivative tells the whole story of the motion. Imagine you're walking along a graph from left to right. A critical point is any spot where your walk momentarily levels out, the slope under your feet is exactly zero, or where the path suddenly has no clear slope at all, like a sharp corner or a break. In the language of our slope detector, the derivative f prime of x, these are the x values where f prime is zero or does not exist. We call them critical points because they are the only places where the graph can possibly switch from going uphill to downhill, or vice versa. They are the candidates for the tops of hills and the bottoms of valleys. Why do we care about these special points? Because they answer one of the most practical questions in calculus: where does something reach its maximum or minimum? If you're designing a can to hold the most volume with the least metal, or finding the best angle to launch a rocket, the answer always lies at a critical point. By finding all the critical points and checking the slope on either side, we can sketch a rough uphill-downhill map of any function without plotting every single point. It's like knowing the peaks and valleys of a mountain range from a simple elevation profile. You instantly understand the whole landscape. Here's the step-by-step recipe. First, take your function and find its derivative, f prime of x. Set that derivative equal to 0 and solve for x. These are your critical numbers where the slope is flat. Also look for any x values where the derivative is undefined, like a sharp point. Next, draw a number line and mark all these critical numbers on it. They split the line into intervals. Now, pick any test number inside each interval and plug it into f prime of x. If f prime is positive, the graph is going uphill on that whole interval. If it's negative, it's going downhill. A sign change from positive to negative means you found a local maximum peak. A change from negative to positive means a local minimum valley. No sign change means a flat plateau. Let's put this to work on a real function, f of x equals x cubed minus 3x. First, we find the derivative using our slope detector rules. The derivative of x cubed is 3x squared, and the derivative of minus 3x is minus 3. So f prime of x is 3x squared minus 3. We set that equal to 0. Dividing by 3 gives x squared minus 1 equals 0, so x squared equals 1. Our critical numbers are x equals negative 1 and x equals 1. Now we test intervals. For a number less than negative 1, like negative 2, f prime is positive 9, so the graph is rising. Between negative 1 and 1, say at 0, f prime is negative 3, so it's falling. For numbers greater than 1, like 2, f prime is positive 9 again, so it's rising. The sign goes positive negative positive. That means at x equals -1, we switch from rising to falling, a local maximum peak. We already know that the first derivative, f prime of x, tells us the slope of a graph at any point, how steep it is. But slopes themselves can change. The second derivative, written f double prime of x, is simply the rate at which the slope is changing. Think of it as the slope of the slope. If the slope is getting steeper, the second derivative is positive, and the graph bends upwards like a cup holding water, we call this concave up. If the slope is getting flatter or more negative, the second derivative is negative, and the graph bends downwards like a frown, concave down. So while the first derivative tells you if you're going uphill or downhill, the second derivative tells you if the hill is getting steeper or leveling out. Why do we care about how bendy a curve is? Imagine you're driving a car along a winding road. The speedometer shows your speed, that's the first derivative of your position. But the feeling of being pushed back into your seat or thrown forward, that's the second derivative, how quickly your speed is changing, or acceleration. In math, the second derivative helps us tell the difference between a hilltop and a valley bottom when the slope is 0. At both, the first derivative is 0, but the bend is different, a peak bends down, a valley bends up. It also lets us find the exact moment a curve switches from bending one way to the other, like the point on a roller coaster where you go from being pulled down into your seat to floating up. Let's build the second derivative from what we already know. Take a function, like f of x equals x cubed minus 3x. Its first derivative, f prime of x, is 3x squared minus 3. This is a new function that gives the slope at any x. Now, just as we found the slope of the original curve, we can find the slope of this slope function. We take the derivative again. The derivative of 3x squared is 6x, and the derivative of minus 3 is 0. So the second derivative, f double prime of x, is 6x. Now look at what this tells us. When x is positive, say x equals 1, f double prime is 6, positive. That means the slope is increasing, so the curve bends upwards like a cup. When x is negative, say x equals minus 1, f double prime is minus 6 and negative. The slope is decreasing, so the curve bends downwards like a frown. The second derivative is simply a sign detector for the bend. Let's use the second derivative to find a special point on a roller coaster track. Imagine the track's height is given by our function f of x equals x cubed minus 3x. We want to find the point where the bend flips, where you go from being pulled down into a frown shape to being pushed up into a cup shape. This is called an inflection point. To find it, we set the second derivative equal to 0, because that's where the rate of slope change is momentarily 0 before switching sign. Our second derivative is 6x. Setting 6x equal to 0 gives x equals 0. At x equals 0, the original function gives a height of 0. Let's check the bend. Just to the left, at x equals minus 1, f double prime is negative 6, so it's concave down, a frown. Just to the right, at x equals 1, f double prime is positive 6, so it's concave up, a cup. Imagine you're a detective. You've learned to find individual clues about a function, where it lives, where it crosses the axis, where it climbs or falls, and how it bends. But a single clue doesn't solve the case. The full sketching strategy is your complete detective's notebook. It's a step-by-step recipe that combines every clue we've learned: domain, intercepts, asymptotes, the first derivative story of increasing and decreasing, and the second derivative story of concavity, and turns the raw formula f of x into a clean, labeled sketch of the curve. It's the master plan that takes you from I have a pile of facts to I can see the whole shape. Why go through all these steps? Because a graph isn't just a wiggly line, it's the answer to the question, what does this function actually do? If you only know a function is increasing, you don't know if it's curving gently like a hill or shooting up like a rocket. If you only know it crosses the x-axis, you don't know if it turns around there or just keeps going. The full strategy reveals the whole story at once. This is exactly what you need in physics and engineering to understand how a planet's path bends, or how a bridge will sag under weight. It turns a mysterious equation into a predictable, visible shape you can reason about. Let's build the strategy step by step for our example. F of x equals x cubed minus 3x. Step 1. Find the stage where the function lives. This is a polynomial, so the domain is all real numbers, no restrictions. The y-intercept is at f of 0, which is 0. For x-intercepts, we solve x cubed minus 3x equals 0, factor out an x, and get x times x squared minus 3 equals 0. So the curve crosses at x equals 0, and at x equals plus and minus root 3, about plus and minus 1.7. Step 2. Find the walls. Polynomials have no asymptotes, so our curve is free to roam everywhere. Step 3. Find the hills and valleys using the first derivative. F prime of x is 3x squared minus 3. Setting this to 0 gives x equals plus and minus 1 as critical points. We use a number line test. Plugging in x equals negative 2 gives a positive slope, so it's increasing. Let's put it all together and sketch our function. We draw our axes. We plot the intercepts, the origin, and at about 1.7 and negative 1.7 on the x-axis. We plot our critical points, the local maximum at negative 1, 2, since f of negative 1 is negative 1 plus 3, which is 2, and the local minimum at 1, negative 2. We mark our inflection point at the origin. Now we connect the dots, but not with straight lines, we use the slope and curvature information. Coming in from the far left, the function is increasing and concave down, so it rises and bends like an arch. It hits our maximum at negative 1, 2, then must decrease. It's still concave down until the origin, so it falls, bending like a frown. At the origin, the curvature switches to concave up, like a cup, while the function continues decreasing to the minimum at 1, negative 2. After that, it increases, now concave up, soaring off to the right. Imagine you're walking toward a wall, but with each step you only cover half the remaining distance. You get closer and closer, but you never actually bump into it. That's exactly what an asymptote is for a graph. It's an invisible straight line, either horizontal, vertical, or slanted, that the graph approaches as it runs off to infinity. The curve gets arbitrarily close to this line, so close you couldn't fit a single atom between them, but it never actually touches or crosses it. Think of it as the graph's permanent, unreachable goalpost. Why do we care about lines the graph never even touches? Because they tell us the story of the function's behavior at the extremes, what happens when x gets huge, or when the function itself blows up. A horizontal asymptote reveals the long-run trend. As time goes on, does the temperature of your coffee settle to room temperature? A vertical asymptote marks a forbidden zone, a value of x where the function simply cannot go, like the speed of light for a massive object. In our sketching strategy, finding asymptotes is like drawing the frame of a house before putting up the walls. They give us the big picture skeleton, so we know the overall shape before we fill in the details with derivatives and critical points. So how do we actually find these invisible lines? It all comes down to limits. For a horizontal asymptote, we ask, what value does f of x creep toward as x runs off to positive or negative infinity? We write this as the limit of f of x as x approaches infinity. If that limit is a finite number L, then y equals L is our horizontal asymptote. For a vertical asymptote, we look for an x value where the function goes completely wild, shooting up to positive infinity or down to negative infinity. This happens when the denominator of a fraction is 0 but the numerator isn't, creating a forbidden x equals a line. For a slant asymptote, which occurs when the numerator's degree is exactly 1 more than the denominator's, we compare growth rates by doing polynomial long division. The quotient, ignoring the remainder, gives the line the graph hugs at the extremes. Let's make this concrete with a real-world problem. Suppose you make a hot cup of tea at 80 degrees Celsius and leave it in a room that's 20 degrees. Newton's law of cooling tells us the temperature difference between the tea and the room halves every 10 minutes. So the temperature function is T of t equals 20 plus 60 times 1/2 to the power of t over 10. As time t goes to infinity, 1/2 to the power of t over 10 shrinks to 0. So the limit of t as t approaches infinity is 20 plus 60 times 0, which is 20 degrees. The graph has a horizontal asymptote at y equals 20. The t never actually reaches 20 degrees, it just gets closer and closer, forever. This asymptote is the room temperature, the ultimate fate of the t. We found it by taking the limit at infinity, and it gives us the long-run behavior of our cooling curve. We have learned to sketch graphs and find slopes and curvatures. Now we ask, why do we actually do this? A graph is not just a pretty picture, it is a story of how something changes. The peaks on the graph are the moments when something reaches its highest value, or maybe a company's profit, or a ball at the top of its flight. The valleys are the lowest points, the minimum cost to build a box, or the least material needed for a can. And the curvature, whether the graph bends up like a smile or down like a frown, tells us how fast the change itself is changing. So graph sketching is really a tool for finding the best possible outcome in a real situation. It turns a formula into a shape we can read, and that shape answers practical questions. Where is the maximum? Where is the minimum? How do I get there? This matters because in the real world, we are always trying to find the best version of something. A business wants to set a price that gives maximum profit, not too high, because then nobody buys, and not too low, because then you lose money on each sale. A physicist wants to know the highest point a rocket reaches, or the path that takes the least time. An engineer designing a soda can wants to use the least aluminum to hold a fixed amount of drink that saves millions of dollars. All of these are optimization problems. And the amazing thing is, they all boil down to the same math: find where the graph peaks or dips. The derivative tells us where the slope is 0, those are the candidates for the best point. The second derivative tells us whether it is a peak or a valley. Let us see how this works step by step. First, we take a real situation and turn it into a function. Imagine we want to build an open box by cutting squares from the corners of a flat sheet and folding up the sides. The volume of the box depends on the size of the cut-out square. That is our function, volume in terms of cut size. Second, we find the derivative of that volume function. The derivative is the slope, it tells us how the volume changes as we change the cut size. We set that derivative equal to 0. Why? Because at the very top of the volume graph, the slope is flat, 0, just for a moment before it starts going down again. Those points where the slope is 0 are our critical points. Third, we check the second derivative at those points. Let us solve a concrete problem together. We have a flat square sheet of cardboard, 12 inches on each side. We want to make an open box by cutting out a square of side length x from each corner and folding up the flaps. What size x gives the biggest box? First, we write the volume. The base becomes a square of side 12 minus 2x, and the height is x. So volume V equals x times the quantity 12 minus 2x squared. We take the derivative, using the product rule and chain rule we learned earlier. Setting v' of x to 0 gives two critical points x equals 2 and x equals 6. Now x equals 6 would mean cutting out half the sheet, the base would be 0, so volume 0. That is a minimum. The second derivative at x equals 2 is negative, confirming a maximum. So the best cut size is 2 inches.